Hi guys, in this video we're gonna talk about the neuroanatomy of the basal nuclei. So what is basal nuclei? Guys, remember that the cerebral cortex was formed of a gray cortex at the outside and white matter in the inside. So they found a group of gray masses at the base of the brain. So they started to call them basal nuclei, okay, because they are a group of cell bodies at the base of the brain. So they are typically gray matter masses at the base of the brain. What are these nuclei? We have one called the caudate nucleus. The caudate nucleus, okay? Caudate nucleus. It goes all the way and it ends as these two mammillary bodies, but functionally it's related to the basal, to the limbic system. So we don't usually explain it with the basal nuclei. So this is the caudate nucleus. And the lentiform nucleus looks like a lens, okay? And the caudate is kind of wrapping around it. So you have the caudate nucleus and you have the lentiform nucleus. And down here inside, you have the thalamus. And why do we have these masses? Because these masses are actually separated. They are there in the base of the brain. They control our motor function, and they help you initiate movement, and they help you to have your emotional responses to stimuli. And they are also separated by the descending tracts from the cortex, the corona radiata. They will be kind of interrupted by the descending corona radiata into medially the caudate nucleus and thalamus, and laterally the lentiform nucleus. Okay, so so if you guys look at this very nice diagram from the base of the brain, you will see, sorry, this is from the top because I can see here the head of caudate. So the head of caudate, and it has a head, it has body, and it has a tail down, and this is down the thalamus, and laterally is the lentiform nucleus. And why there is a gap? Because there is a descending cortico-spinal, frontopontine, corticopontine, all the tracts coming from the cortex are descending and separating them into medial group and lateral group. The medial group is going to be the caudate and the thalamus, and the lateral group is the lentiform nucleus. And the lentiform nucleus is formed by two nuclei, the putamen and globus pallidus. Why do we divide them? Because every one of them will have different function. Okay, so remember that lentiform nucleus is laterally. We call it putamen and globus pallidus, and medially we have the caudate nucleus. And at some point, the caudate nucleus is going to be continuous with the outer part of the lentiform, which is the putamen, and that is what we call the nucleus accumbens. I'm going to show you that as we proceed. And this has a role in emotion and reward, and that is going to be explained in the limbic system. Okay, guys, there is another name for those guys. It is basically okay, so this is again the same thing. It's not the different name. It's shown here. I'm showing you guys the idea I told you, that those gray matters at the base of the brain, which is the caudate nucleus and the lentiform and the thalamus. Thalamus is gonna be medial and the caudate, and the lentiform is gonna be laterally, which is the putamen and globus pallidus. And if you think about the caudate nucleus that has a head, body, and tail as a mouse, remember that your the cheese of that mouse is going to be the lentiform nucleus, or the outer part of the lentiform, which is the putamen. Why this is important? Because I want you to know that at some point anterior, if we take a coronal section anteriorly, you will find that the caudate nucleus is continuous with the outer part of the lentiform, the putamen. And this continuation is what we call the nucleus accumbens. This is where the mouse is going to eat the cheese. Okay, the continuation here is going to be the nucleus accumbens. Okay, now there is another name for that, is what we call it the corpus striatum. Okay, where is the corpus striatum? Here, the corpus striatum. Why do we call it corpus striatum? Because it's striated by those descending tracts. You guys have connections coming in and out from the cortex, because cortex is our big boss. We have the optic radiation coming there, the auditory, we have the descending motor tracts, ascending sensory tracts. So that is basically interrupting my bodies here. So we call it corpus striatum because it's interrupted by the internal capsule. All right, so we call it corpus because it's a body striatum. It's striated and stripped by the tracts coming up and down. Okay, guys. What was there? Yeah, nothing. It's just that the terminology. Oh, all right. So this is if we take a coronal section and we look at the coronal section in the cerebral cortex, we will see that, like I told you guys, those descending tracts are going to divide the whole story into caudate and thalamus medially and the lentiform nucleus laterally. Okay, this is general talking, and I will tell you how you will be able to identify those structures and cross sections of the brain. I have a story that I tell to my students for them to remember the name of the nuclei in a cross section of the brain, which is the putamen is basically your Batman that is sitting on the globe. Okay, so putamen is the darker gray matter that is laterally, of course, you guys, this is the lentiform nucleus. Laterally, you have a darker colored putamen, and the putamen is sitting on the globe. And we have globus pallidus externus and internus. Okay, so remember, the lentiform nucleus is laterally. Those guys are laterally, and what is outside is the putamen. The outside is the putamen, and the globus pallidus is internus. This is how you will come to know how to identify the basal nuclei parts in the coronal section and also in horizontal section of the brain. Putamen is sitting on the globe, outside and inside. Now, how will you remember the caudate nucleus and thalamus? Think about the cutie cat story. You guys, to me, coronal section of the brain looks like a cutie cat. Cute cheeks. These are the caudate nucleus. These are the cheeks that are bulging into the eyes of the cat. The cat eyes are the lateral ventricles. These are the spaces, all right? These are the lateral ventricles. And caudate nucleus is basically the cheeks that are bulging into that. So if you guys can see here, gray matter bulging into the cat eyes, this is the caudate nucleus. Okay, here outside you have the putamen and globus pallidus, externus and internus. This is the putamen on the globe. Remember what else did we say? We said that the descending and ascending tracts are going to divide my basal group of nuclei cell bodies into medial group and lateral group. The medial group is going to be the thalamus down and the caudate nucleus up. What bulges into the cat eyes is the cutie cheeks, cat, C, caudate nucleus. What is down here, the gray matter, is your thalamus. What is lateral, putamen on the globus pallidus. Okay, guys? And here, this is the substantia nigra. This is part of the midbrain because substantia nigra has a very important role in the controlling of the circuitry of the basal nuclei connections. And that we will talk about as we proceed and talk about the function of the basal nuclei. Now, if we have the horizontal section, if we take a horizontal section and we try to look at this, again, we will have the ventricles. The cutie cheeks are going to be my caudate nucleus. And then the gray matter in the medial part is going to be my thalamus. Okay, so caudate nuclei, thalamus here, thalamic nuclei. And laterally, we will have the putamen, the darker, the Batman sitting on the globe. The darker gray matter area is going to be the putamen, and this is the globus pallidus, externus and internus. And what separates them is actually the internal capsule, because remember that those tracts are what divided my basal nuclei into groups. So I have the descending, the corticospinal tracts, as they descend from up to down, we will find them separating these into medial and lateral group. Okay, guys? So the caudate nucleus and thalamus will be medially, the lentiform nucleus will be laterally. So this is what divides them, which is the internal capsule. It has anterior limb, it has genu, and it has posterior limb. This is the descending, the internal capsule, the ascending and descending tracts. And the thalamus, remember, it was in the center, and the caudate nucleus was in the center, the QT cheeks. Okay, guys? Perfect. And here I wanted to show you, if we take a section anteriorly, and you can see that the medial guys are continuous with the lateral guys. This continuation is basically what we call the nucleus accumbens. It's where the mouse, the caudate nucleus, head of the mouse, is mouth of the mouse is eating the cheese. Okay, so the continuation between the medial guys and lateral guys is what we call the nucleus accumbens. Okay, and that has an important feature in um, the and that is having an important feature in the limbic system. Okay, so these are more sections. They are not so much good, but at that point here, and that was actually the nucleus accumbens is important for limbic system function. Now, what is the function of basal nuclei, and what is the difference between cerebellum and basal nuclei? Now, guys, basal nuclei is going to help you to initiate the movement, the smoothness of the movement. It has important role in cognitive function and in limbic system itself. So there is connections between the cerebral cortical areas and the basal nuclei in order for us to initiate movement, and in order for us to have some cognitive functions, and also for the limbic circuitry. And in the limbic circuitry, it's basically important because it activates the motor areas to active. This is the link that causes you to have facial expressions, you guys, and body language. It is the connection that brings the emotions from the limbic system to the motor areas in your cortex, and based on the registered memories about something, you are going to recall that into a facial expression and body language. So that is the limbic part of the basal nuclei. And the cognitive is when you try to associate something happening with the registered information you have in your associated association areas in your brain. And in order to do a motor function, in order to initiate a movement, you have connection with basal ganglia to give you a feedback into the motor area and give you the push to initiate for a movement. Okay, now we're going to talk about the motor circuit into more details, because it's important for you guys to know how do we unlock and start a movement, and why basal ganglia is very important to initiate a movement. Now, before we start about talking about the circuitry of the basal nuclei, I want you guys, let's make a deal together. I want you guys to know that if you have neurons, firing neurons coming from the cortex or any cortical areas, including the thalamus, subthalamus, this is gonna be glutamatergic. It's gonna be excitatory. Okay, so positive charged. If I have anything coming from the basal nuclei, it's gonna be inhibitory. Why is that? Because you guys, basal ganglia is working right now when you are trying to listen to my video and you don't want to do any movement, silently listening to me. Now, if you find some important information and you want to write it down, the basal ganglia should be unlocked, because as you are getting sensory stimulus by my talking and my visual pictures I'm giving you, your cortex is very hyper. It wants to react to what I'm doing. But thanks to the basal ganglia, because it makes you sitting at rest and listening to me carefully. When should we stop basal ganglia? We should stop it when we want to react, when we want to write down a piece of information that is very important that we've learned from this video. In that case, your motor cortex is going to send to the basal nuclei and tell them, please, can you stop stopping me from movement? I need to write down important information. I don't want to sit silent now. In that case, we have to turn off the basal ganglia work. We can tell it, please, can you little bit turn off your inhibition on me because I want to do a function. Okay, and that is going to be explained into more details. So what happens is from the cerebral cortex, you guys know, as we all know, all the time, we are forming those corticospinal tracts because we need to do a movement. As we think about the movement, remember that we were having some information going to the cerebellum and asking them how should we prepare for the movement. As we do that, we are also receiving to the somatosensory area a lot of stimulations. And from there, we have primary motor area that wants to send motor supply, and it wants to move my muscles all the time. So cortex is getting stimulated all the time by the surroundings, and that wants to do a movement. But before we do the movement, we will go to the striatum, and that striatum is going to be the caudate and putamen. These are the global input guys. They are going to be the receiving chambers, the receiving guys for all information from the cortex, and the globus pallidus is going to be the sending chambers or sending guys, okay, to the basal striatum, the basal nuclei as a whole. Okay, so cortex wants to do a movement. It will send those excite. Remember, we had a deal that cortex is sending positive charge. Now, the direct pathway, we have direct pathway and indirect pathway. Remember, indirect inhibition. Okay, they will inhibit movement. So in the direct pathway, we will do movement activation. So now we want to do a movement. Okay, now we want what should we do in the direct pathway? Cortex wants to do a movement. It will send some information to the caudate putamen, activation to them. It will tell them, please, I want to do a movement. This is the direct pathway. Now, when you do positive charge to the caudate and putamen, guys, basal nuclei, remember, they are negative charge. So if I activate them, they will send negative charges to the globus pallidus internus, negative. So if I send negative to the globus pallidus internus, which is also negative, this is going to be positive. It means I'm going to stop the inhibition on thalamus because now I want to do movement. Basal ganglia at rest is stopping the thalamus from doing the movement, because you remember, guys, thalamus is the secretary of the cortex. Thalamus, it has all the information coming to the cortex. So if the thalamus is active, it will make the cortex to do a movement. Globus pallidus internus is holding the thalamus from doing movement if we don't need it, if it's unwanted. But if I need to do a movement, I have to stop globus pallidus internus from holding my thalamus back. This is going to be by sending positive charges to the caudate, and then the caudate are going to send negative to the internus. Negative on the negative, inhibition of the inhibition means excitation. I will excitate the thalamus. Once the thalamus is excited, it will excitate the cortex to do the movement. I will have the corticospinal tracts coming to my limb muscles, and I will be able to write down the important information in that lecture. Okay, so in the direct pathway, we have activation. We are working on the main people of the basal nuclei. Who are the main people? Caudate nucleus, putamen, globus pallidus internus. Cortex is active. It will go ahead to caudate and putamen. Please, I want to do a movement. Can you stop globus pallidus internus from stopping the thalamus? It will go and stop it. Once it stop it, it will stop the inhibition. Once we inhibit the inhibition, we will have excitation to the thalamus. Thalamus will go ahead and activate the cortex, because cortex, thalamus, and subthalamus are all glutamatergic. They are all excitatory in nature. Once I get that positive to the cortex, I will go ahead and form my tracts, and I will have a movement. That will give me movement. Now, what will happen if I don't need a movement? Now, let's say this is what happens in normal circumstances, guys. If you guys listening to me right now, and you don't need to write down anything, basal ganglia is working the way that we will explain now. Inhibition, the indirect pathway is going to happen. Now, the cortex of you guys right now, if you don't want to write any information behind me, following what I'm saying, the cortex is getting activated by my sound and it's getting activated by my pictures. So it is all positive. So it goes all the way to the caudate and putamen, and it tells it, I want to move. Now the caudate and putamen, they don't want to move because you don't need to move now. Okay, it's getting stimulated and you need to listen to me. There is no major information that you need to write down. So movement is an unwanted movement at this situation. So caudate and putamen will tell themselves, what can we do? If we get activated and we go to the internus, we will stop the internus from inhibiting the thalamus and we will get movement, but we don't want to do movement. It's not needed now. They will make a deal. They will say, okay, fine, we are getting activated, so we will send this activation into the externus, and the externus, we will get activated, so we will send inhibition, and that inhibition we will redirect it to the subthalamic nucleus because we don't want the inhibition on thalamus to happen. So our inhibition is not going to go to the internus, it's going to go to the externus. Externus will tell them, okay guys, I got your back, I will send the inhibition you are sending me to the subthalamus. So your inhibition is going to inhibit me, and inhibition on inhibition is going to excite the subthalamic nucleus. So now I can stop your inhibition from going to the internus, and your inhibition and my inhibition are going to cancel each other's, and we will redirect it to the subthalamic nucleus. Subthalamic nucleus is part of the cortex. It's excitatory in nature. It will go ahead and excite the internus. If the internus is excited, internus is holding the thalamus back. It is inhibiting the thalamus to do unwanted movement. So that way we will inhibit the thalamus and the cortex is not going to do any movement if we don't need it. Okay, guys? So this is the indirect part of our basal nuclei. So remember, if we want to do a movement, we have the major guys: cortex, caudate putamen, internus, and thalamus. If we want to inhibit movement, which is when we don't need that movement, putamen and caudate are going to make a deal. They will send the inhibition to the externus. Externus inhibition with their inhibition will cancel each other's, and they will redirect it to the subthalamic nucleus. Subthalamic nucleus will excite the internus, and the internus is already inhibitory in nature, so it will inhibit and hold the thalamus back, and that inhibition will hold the cortex from doing the unwanted movement. So indirect pathway, inhibition, no movement. All those guys are coming to the scene. But if I need to do a movement, it's going to be direct. Cortex will excite the major receiving chambers, caudate and putamen. Once we excite them, their negative charge will be put into the negative of internus, and those two will be positive on the thalamus, and we will have movement. Okay, guys? So in that case, we will have inhibition. Now, what is the rule of the substantia nigra in that thing? Broadly talking, you guys, the substantia nigra pars compacta, it has a dual role. But I want you to know one thing before we dive deep into the substantia nigra, because I don't want you to get confused. Substantia nigra pars compacta, it has dopamine. The dopamine is going to facilitate the whole stories we talked about them previously. They are going to facilitate the activation of the direct pathway. They are going to facilitate the inhibition of the indirect pathway to do a movement. Broadly talking, substantia nigra dopamine is going to help me do a movement. How can I do a movement? By sending dopamine, by activating direct pathway, by inhibiting indirect pathway. Why are you activating the direct pathway? Because I want to do a movement. Why are you inhibiting the indirect pathway? Because I want to inhibit the inhibition, because I want to do a movement. So broadly talking, before we dive deep, substantia nigra pars compacta dopamine, it acts as excitatory to the direct pathway, inhibitory to the inhibitory pathway, because at the end, I want to do a movement. So what happens here is the substantia nigra, Pars compacta, it's gonna have two receptors. The D1 receptors is going to activate the direct pathway. It will depolarize the D1 receptor. It will activate the direct pathway, and it will inhibit the indirect pathway. If I activate the direct pathway, it means I will move from the receiving chambers to the globus pallidus internus, and then I will inhibit the inhibition and I will do movement. And if I inhibit the indirect, it means the whole story that inhibits movement is going to be cancelled. At the end, I will have a movement. At the end, I will do activation. So dopamine helps me to do movement by activating the direct pathway and inhibiting the indirect pathway. Okay, guys, what will happen if we have a problem with them? If I have a problem in patient with Parkinson, I'm not going to be able to activate the direct pathway, and I'm not going to inhibit the inhibitory pathway. So what will happen? The direct pathway is not working. It means I cannot do movement. And what else? The inhibitory pathway is not going to be inhibited. So it will stop me from doing movement. So the direct pathway is going to be off, which helps me to do movement. And the indirect pathway is going to be on, which is inhibiting me from doing movement. Eventually, I'm not gonna have movement. Okay, guys, can you see this is faded pathways? I'm not gonna get anything. What's gonna happen? Rigidity. The patient is trying to do a movement, and it's telling the receiving people, you guys, please stop the globus pallidus internus. I want to do a movement, but it cannot do that because I don't have dopamine. Dopamine was the key. It was my key to activate the direct pathway. It was my key to inhibit the indirect pathway to do the movement. Now, I cannot stop the globus pallidus internus from stopping the thalamus from doing the movement. Globus pallidus internus is very active now. It is holding my thalamus back. I cannot do movement. I will have rigidity. I will have bradykinesia. Okay, so in that case, I have a problem. I cannot do a movement. Okay, now what happens? Why do I have resting tremor then? Remember, guys, I told you the function of the basal ganglia is to stop the unwanted movement from happening. Now, in the inhibitory pathway, it is active to stop me from doing the unwanted movement. And in that case, the inhibitory pathway was active to inhibit. Now, in that patient, if he's getting a lot of stimulation from the surroundings, the basal ganglia is not working to inhibit the unwanted movement. That will cause what we call the resting tremor. What is the difference between resting tremor and the intention tremor we have in the cerebellum? You guys, cerebellum moves when we are doing the movement in motor execution. It is acting by inhibiting and exciting the extrapyramidal tracts to fine-tune the movement, to tell me how exactly I should contract my muscle to reach to that place. The problems with cerebellum will appear when you ask the patient to do a movement. We call it intention tremor. When the patient intends to hold a cup, he will be having a tremor while doing the movement. It's not going to happen at rest because we don't ask cerebellum for anything at rest. Cerebellum only works when we're doing the movement to fine-tune the movement. But basal ganglia, it works at rest. This basal ganglia, it's what makes you to sit now without moving your body because you don't need that movement. Basal ganglia works to hold the thalamus back from getting affected by the stimulus coming from the cortex. If your basal ganglia is not working, the patient is going to have a resting tremor because you cannot stop the unwanted movement from happening. So if you have basal ganglia problem, you will have problem from stopping the unwanted movement at rest, you have a problem from canceling the inhibition on thalamus when you want to do a movement, having rigidity and bradykinesia when you want to stop the basal ganglia. So this is where the basal ganglia will appear to us. Okay, so basal ganglia, you need it to inhibit the unwanted movement at rest, and it is needed to cancel the inhibition on thalamus when you want to initiate movement and you want to smoothly do movement. So that will end up having rigidity and bradykinesia. And the other problem, when you cannot stop the unwanted movement, this will end up having resting tremor. So this is going to happen with basal ganglia problem if you don't have dopamine, which is the facilitator of both pathways. And every pathway is going to be activated based on where we need it. Okay? And now let's talk about the blood supply. You guys remember the blood supply of your brainstem? We talked about the circle of Willis, and we said that we have the vertebrobasilar system. Okay, guys, we have two vertebral arteries forming the basilar, and circle of Willis was formed by two posterior cerebral arteries. And now we have the carotid system. Okay, the carotid system will take care of everything. The vertebrobasilar system takes care of the posterior everything, and anything anterior, deep, and outside is going to be taken care by the internal carotid. Internal carotid, you guys, we said previously that it gives you the middle cerebral arteries. So it gives you the middle cerebral arteries, and it also gives you anterior cerebral arteries, and it gives you internal carotid. Internal choroidal, anterior, we have something called anterior choroidal. Why choroidal is important? Because that forms choroid plexus and ventricles. That gives you the CSF. And it's also a deep blood vessel that will participate in the blood supply of the basal nuclei. Now, remember that when we explained previously the blood supply of the deep structures, we said that we have something called lateral striate or lenticular striate artery and medial striate or artery of Hübner. One of them is going to be by the middle cerebral artery, and one of them is going to be by the anterior cerebral artery. Okay, so if you guys look at the internal carotid, the internal carotid artery gives you the internal carotid artery gives you the middle cerebral artery. Middle cerebral artery will give you the lenticular striate. Major blood supply is coming from the lateral striate or lenticular striate. The most of the blood supply comes from the middle cerebral artery, the lenticular striate. However, from the anterior cerebral artery, okay, I cannot change the color. From the anterior cerebral artery, you have the medial striate or the artery of Hübner, which gives you a small branch. If you look at a cross section like that, okay, so you will find that the anterior cerebral artery will kind of give you a medial striate, and mostly talking, most of the blood supply is coming from the lenticular striate from the middle cerebral artery. Okay, and then the anterior choroidal is a deep branch, so that will give you also, which was the branch from middle cerebral artery. Okay, so remember we had the internal carotid arteries. Internal carotid was giving me middle, internal carotid was coming from down, so it will give you middle cerebral artery, and then it will give you anterior cerebral arteries. Okay, so anterior cerebral arteries. From the anterior, you will get medial striate, small contribution, and from the middle, you will have the lenticular striate or lateral striate, and also from the internal carotid, you have the anterior choroidal. So these are the branches that you have in the deep structures of the basal ganglia blood supply. Okay, thank you guys for watching. I hope you grasp the concept of the basal nuclei, and see you in the next videos.